Hi everyone. Sorry for the late start, slightly late start. 1 second. Just trying to iron out an audio issue, but it looks like it's fine. So today is going to be focused on, on answering questions that come into the Slack, for sure, but also on problems related to the technical interview. So I'm just going to invent a number of problems, and we'll take a look at those. And just to start off with, let's talk. I have a question in here about while loops. Would it be possible to talk about while loops in particular? I've been struggling with conditional checks and open-ended problems. So let me just take a peek at the lesson that you're referring to, and then I'll just code out, code something out that hopefully will kind of explicate the idea of an open-ended problem and a conditional check. So the conditional check itself is just this, what we're seeing here, while x is greater than 0, something like that. That's the conditional check, right? This is going to resolve to true or false, right? And it doesn't look great, it's all pixelated, but this is going to resolve to true or false. And as long as it's true, this while loop will persist. Now, turns out that you can write a while loop like this, while true, and let me go ahead and show you something just simple. I'll say I gets 0, and we say while true. I'm going to say I plus gets 1, and then if I is greater than 20, we break. So this conditional check, this is an infinite loop essentially, right? This is us performing this operation infinite times. However, we do have an exit condition. So this exit condition, when I becomes greater than 20, we're going to break. And when we look at I at the end, I'm in a Jupyter Notebook, by the way, so I don't have to put a print statement here to see the output. Notice I is 21. So when I is 20, it passes by this. If we said I is greater than or equal to 20, then we'd break, and I would be 20, right? Kind of basic logic there. This break statement sits under a conditional check, but it could actually sit there, and that's not really different. So, we could have a couple different conditions, and we could do, we could have a conditional check here alongside the while loop, or we could do, an if statement down here, or we could do like a compound conditional statement where if I is greater than 20, or let's say we had some other variable, if j is evenly divisible by, I don't know, let's say 7, right? So we could do that to have a compound statement in our while loop. That would be fine as well. In general, you do want to put your conditional check here, right? Although there's nothing wrong with saying while true and then having an exit condition is what I tend to call these, or a break statement under an exit condition. So that's just the idea of a conditional check. Let's consider an open-ended problem. I don't know why that didn't delete. Okay, so what do we mean by an open-ended problem? This can look a number of ways, and I'm just going to invent one. So let's say we have 2 dice. We have a 6-sided die and a 30-sided die. Okay, so with a 6-sided die, let's say 6. Oh, can't do that. I'll say 6-sided. You can't start a variable name with a number. I almost did, but you can't do that. So six-sided is going to get a choice from, I could put just 1, 2, 3, 4, 5, 6. What I'm going to actually do here, though, is list, range, and go from 1 to 6. And I have to do 6 plus 1 because it's, essentially to 7 in order to include 6. And then let's do a 30. Did I say 32? I think I did. Let's do 36. No, yeah. Let's do 36. So let's say 36-sided, and that's going to get a similar thing. We're going to go from 1 to 36 plus 1. Okay. If I want to look at these, well, let's just look at the sum of these. Okay. And name choice is not defined because I did not import it. So from random import choice. So 27 and then 21, 2, 41, 31, 27, 19, 16. So we might ask the question, how many times on average? Yeah, let's think about this. Let's say, let's ask the question, how many times on average, how many times on average does it take to get a roll over 20, over sum 20, okay? So that is a question that we can answer through essentially calling out to some function that's going to get us the sum of a 6-sided and 36-sided die. So I'm going to write that function, and I'm going to call it dice roll. And I'm just going to return the sum of, well, let's do it like this. Let's just return 6-sided plus 36-sided. And so that's defined. If we want to answer this question, how many times on average does it take to get a roll over sum 20, then let's just sort of perform an experiment here. Let's say def analyze dice roll. And let's put a threshold here. So let's say threshold, and I'm going to default that to 20. This is, let's say, threshold. I'm going to say threshold over, okay? And I'm going to make an accumulator called rolls, and I'm going to say while let's set rolls equal to 1, and let's do an initial roll, right? So I'm going to say roll gets dice roll, okay? So while roll is less than 20, we're going to, we're going to increment the roll. So I'm going to say rolls plus gets 1. And I'm going to say, I'm just going to perform this operation again. I'm going to get another dice roll. Okay? And at the end of this, I'm going to return the number of rolls. All right? So if I call this, let's do this. So less than 20. Yeah. Okay. So if I run this, guess one roll. 2, 1, 1, 5, 1, 2, 1, right? So let me just make sure this is doing what I think it's doing. Sometimes I make really simple errors. Let's do that. Okay, 13, 8, 6, 11, so 5. We got something over, let's do over 30. Yeah, let's do over 30 just by default. let's answer a different question just so it's a little more interesting. Okay, there we go. One, while the roll is less than 20. Yeah, so it took 6 rolls to get a roll, and I'll also print the final roll here. So final roll, and let's just put roll. Final roll is 23. Oh, that's, I see my, this is that thing about sort of missing simple logical errors. Okay, there we go. Final roll 31, which is over 30. Final roll 33, which over, okay, so let's say roll equal to or over. I think that's the question we're actually answering. And I think it's a better question. So we can see the rolls, 12, 13, 26, 15. That took 9 rolls, 2, 1, 1. Okay, so this is an open-ended problem, right? This is going to continue until we hit a threshold that we want. You know, pretty simple in that sense. It's we're returning the number of rolls, and what we could do is analyze this and say, out of 1,000 rolls, what's the average? And we're going to settle somewhere for a given threshold. So why don't we just do that? This is, but long story short, this is an open-ended problem because we don't know how many rolls it's going to take in order to get a sum that is over 30, right? So yeah, in terms of analyzing this, that's not too hard. We can simply call to this a certain number of times. So let's say I'm gonna just do this in a comprehension. No, you know what? I'll write a function. Okay, so analyze dice roll, and let's say, well, nah, I'll just do it in a comprehension. No, I'll do it in a for loop just to keep it easy. So, so this is number of rolls to meet the threshold, and I'll say for roll, actually for whatever in range, and we'll do this 1,000 times. Num rolls is going to have appended to it this analyze dice roll with a threshold over 30. Okay, so that makes sense. And what we can do here is say the sum of the number of rolls divided by the length of the number of rolls. And that'll get us, oops, I'm still printing stuff. Let me just go ahead and not print. It's not actually doing anything for us here. Okay, so 3.5, 4, 3.4, 3.2, 3.4, 3.3. You know, if we were to perform this a number of times, we could probably narrow in on our expected number of rolls to achieve a threshold over 30. It's looking somewhere around 3.4 something. But yeah, long story short, I know I took that a little bit further, but this is an open-ended problem. We don't know when we're going to arrive at a roll, you know, a roll that's over a certain value. And this might be a very simplistic way to think about it, or a very simplistic problem. There are more complex problems that are open-ended, right? You know, just keep in mind that an open-ended problem is something where we don't know the number of times we have to perform this iteration. In this case, we're returning the number of times that we're performing the iteration, right? If you know how many iterations it's going to take to do something, then you definitely want to use a for loop. There's no reason not to use a for loop in those instances. Okay, so I hope that that's helpful in understanding when and why you would use a while loop. It's you know, my general tendency, my general suggestion is to not use a while loop unless you need to. And there are a lot of instances where you really don't need to. You think you need to or you want to, because it's sort of this it's sort of this primitive form, right? You can literally say while true and you'll have something that loops forever. It's a primitive form, but it's not as performant as a for loop for, you know, sort of lower level reasons on your machine. But it is also a good thing to use for clearly understanding your problem, or, you know, this is an explainable bit of code. Well, we're going to do this until the roll is, until the roll is greater than or equal to the threshold. Cool. So let's look at another question. Could I take a look at the challenge? There's a Bayes theorem challenge. Let me go ahead and look at this. Number 2 in the Bayes theorem lesson. So let me grab that. Oh, did I just open that in a new tab? I did. Okay. Let's just put that back there. All right. So of course, here's Bayes theorem. Let me just, I'll just snag this, put this up in the corner. So you have it as reference. And let's look at challenge 2. Oh, and by the way, I'll do some more while loop stuff in a bit. I'll use some dictionaries to analyze the while loops, because I can find a way to work that into things that look like what's on the technical interview. To be clear, we don't really test you on anything that needs to use while loops in the technical interview. But it's a good tool for when you don't know how many times you need to do something. For anything on the technical interview, it'll be inherent. Like, you'll have a list that you have to process, or you'll have a range of numbers that you're looking at, that you analyze through you perform some function and you analyze it through a dictionary. So you won't be using while loops on the technical interview, but I can make up some problems that look like technical interview problems using a while loop. So I'll do that a little bit later. Okay, so we've got this problem. A recent study was conducted to determine whether there is an increase in a patient's probability of having liver disease if they consume alcohol regularly. The study concluded that a total of 10% of patients, regardless of whether they are consuming alcohol regularly, there's a typo, have a liver disease. The study also determined that amongst those with liver disease, 7% regularly consume alcohol. Finally, the study reported that 5% of the patients taking part consume alcohol regularly. Okay, what is the probability that a random chosen individual from the study has liver disease given they regularly use alcohol? So let me just snag this. And yeah, so let's think about this. I don't know if you looked at the hints already. Oh, what a hint. Apply Bayes theorem. Seems a little obvious that you would apply Bayes theorem here, given that it's a Bayes theorem lesson. We could probably give you a slightly better hint. So I have this over here. I'm just going to close this, and we'll look at this in this Jupyter Notebook, and we'll think about it this way. So let's do this. And one thing that frustrates me about Jupyter Notebooks, one of the things, is that it doesn't allow you to scroll down to get the view even. Like, I just had to put in a bunch of empty cells. All right, so write down what we know. We know the probability that a patient regularly consumes alcohol. Okay, so we know probability that a patient consumes, let's say, just consumes alcohol. Okay, and let's see, what is that? Finally, the study reported that 5% of the patients taking part consume alcohol regularly. Okay, so that's 0.05. That's our probability for that. We know the probability that a patient has liver disease, right? What is that? If they consume alcohol regularly, the study concluded that a total of 10% of patients, regardless of whether they consume alcohol, have liver disease. Okay, so the probability that, I'll just shorten these, consumes alcohol, has liver disease, and this is going to be 0.1. And what else do we know? We know the probability of a patient regularly consuming alcohol given that they have liver disease, correct? The study determined that amongst those with liver disease, given that they have liver disease, 7% regularly consume alcohol. So this is the probability that if they consume alcohol, or sorry, given that they have liver disease, they consume alcohol. Okay, and that is 0.07. All right, so where do we go from there? We could assign letters to these. That's often what you see. So we could call this A, B, and then A given B. I don't tend to do that. I tend to leave it in its present form. Okay. So what do we need to figure out here? We can say the probability. Sorry, we're asking the question: what is the probability that a randomly chosen individual from the study has liver disease, given that they regularly use alcohol? So the question we're trying to answer is the opposite of this. So let's go ahead and I'll just put that. Oh, that doesn't look very nice, does it? Let's do this. Okay. And I'll make this a markdown cell as well. And we're really just trying to kind of invert this question. Oop. What is the probability that somebody has liver disease given that they consume alcohol? If we look at our Bayes theorem formula, we can sort of rewrite this in this form. So the probability of A given B equals the probability of B given A, which we know, which is right up here, right? Multiplied by the probability of A, okay? Probability of A here, sorry, A given B, so has liver disease. Probability of has liver disease, okay? And this is going to be divided by the probability of B, okay? Which is consumes alcohol, right? Yeah, okay. So this is kind of we could say this is a somewhat easier problem than a lot of Bayes problems because we're given the probability of B, all right, right here. The probability of consumes alcohol. We're given that data, or that piece of data. So why don't we just fill this in? And I'm gonna grab this, and I'll just put it down here, and I'll say, okay, what is the probability of consuming alcohol given they have liver disease? That's 0.07. What's the probability that they have liver disease? That's 0.1. What's the probability that they consume alcohol? That's 0.05. So let's just see what that is. 0.14. Let's see if that is the correct answer. I believe it is. Oh, did I not? Let me just put this up here. And let's look at this problem 2. Put that in there and check the answer. And that's correct. Okay. Okay, yeah, and if we look at the explanation here, in this case, like I said, often we'll apply A or B to the specific probabilities, right? The probability of A is the event of patient regularly consuming alcohol. Probability of B is, B is the patient has liver disease. I don't like to do that. I feel like it's easier to see the problem if I don't rename it A and B, but that's really a choice that is in the hands of the person solving the problem. Okay. Yeah. Hopefully that's a good enough explanation in this instance. It's really about, these problems are often sort of textbooky, and it's about looking at them and mapping them out, writing down what you know, plugging that into Bayes' theorem, right? And then if you don't know the denominator, figuring that out with law of total probability. Awesome. The answer for Bayes' theorem had a typo. Yes, it did. Let me take a look at that. Oh, the answer has a typo. What is the typo? 0.1, 0.05. Oh. Yeah, it does. Right, 0.07 times 0.1 divided by 0.05. Oh, I'm sorry. Where's the typo? My apologies. I'm not actually seeing the typo. I thought I saw it. B given A. Ah, right here. Probability of B given A equals probability of A given B times probability of B over probability of A. Yeah, this is why I find this form of writing it a bit confusing. But yes, this is a typo. I might just commit a quick fix on that. It'll just take me a second. So bear with me. I should be able to just fix this. It won't be reflected on the live site right away, but when we pull our changes in, it should be reflected. Thanks for that catch. I didn't notice that. Sort of hard to see. So that's probably of B given A equals probably of A given B. That's what needs to change. Okay. All right. Yeah, so that should be corrected next time we pull from GitHub. Okay. So there's a question here regarding the map function in intermediate Python. Huh. I didn't realize we were using map functions. Is that in... Let's look at challenge 10. Let's go ahead and look at the results of this. So I can walk through what's happening here. This is a really good use of the map function, which I'll just say first. But notice here we have star args. We can pass in as many values as we want to star args. And that's going to turn, so args itself is going to be a list, right? And then we make that list into a set, okay? And the interesting thing here is that we are assuming that set is going to deliver us sorted values. And that might be a safe assumption in the newer version of Python, but I would actually throw in here the sorted function. Or sorry, you know, what I would really do So you can't guarantee order in a set. And that might be a little different in Python now. Let me just... okay, how do I... I'm just going to search for this really quick. Python guarantee order for a set. Just going to check this out. Okay, so we can't guarantee order here, but we are assuming order, which is fine because it seems to be working. I think that's the set is going to not guarantee order, but it's going to try to enforce order, which is what I think we're seeing. Why this is actually in order. At any rate, probably what should happen here is changing this to, I don't know if we can apply sorted directly here. We might not be able to, given that it's a set here, but I'm considering just turning this into a list. Yeah, okay, that worked. Notice we get the same answer, of course, but I just don't trust set to always give me things in order. That said, let's talk about map for a second. So str is a function, okay? Str, we may not think about it that way. We think, oh, well, that's a data type. You know, the string data type. But consider that it's also a function. String is a function. And we can create a string out of the number 45, the integer 45, by just casting it, right? This is a casting function. We can go ahead and do that. So all we're really doing here is we are mapping the string function against all the elements in this list that I have here. So let's do this a little differently. Let's do something like this. Yeah, let's do def. I'm gonna call this double the number. Oh, I know. Double the string number. Is that what I want to do? Yeah, I'll do that. Okay. And we're going to do that for a number. And I'm going to say it's just going to return num string of num plus string of num. Okay. So notice we're casting to a string here, and then we're concatenating. I'm going to take this function, and I'm just going to put it in place here, and let's see what that does for us. Notice, you know, if we take the element 1 and we pass it into double string num, it's going to be the string of the number, so that's 1, concatenated to 1, which gives us 11, right? So that's just two strings that we put together, and it gets us 11. So now, instead of mapping the string function, we're mapping a function that we wrote against all the elements in sorted args. The other thing we could do, right, we could return this. We're printing it here. We could just return it. That's going to get us the same thing, but in the format of a string. We could also... let's consider this. So I'm going to perform this map operation here. And let's see what that gets us when we join sorted args. Notice we were expecting a string, okay? Expected a string instance, but an int was found. Why is that? So what we're doing here when we perform this map operation, we're not actually modifying sorted args in place, okay? So if we want to actually use this, we would need to assign the results to sorted args. So the result of this map function where we map the double string number onto every element of sorted args, that's going to return something into sorted args, and then we can join it. So I hope that clarifies what the map function does. It's simply a function that will take another function and take the properties of that function or the functionality of that function and apply it to every element of a list or a set or whatever you happen to be working with. Okay. So let's think about technical interview stuff. I'm going to put some problems here, and I'm just going to make them up. And if you're watching, try to. Oh, sorry. Let me address this follow-up question. So it's applying the function in parameter 1 against parameter 2. Yes. Yeah. The map function. The map function will take the function that is this parameter 1, this double string number, and it will apply it against the collection in parameter 2. That's exactly right. Okay. So I'm going to just write some problems. And, I'm going to encourage you, if you have a problem, let's say a distributions problem, which I'm going to put a distributions problem up here right now. If you have a distributions problem, try to take that problem and rewrite it with different numbers and then rewrite it into a different scenario, okay? I'm going to say you are sitting on a park bench. On average, 2 out of every 13 people that walks by has, is holding an ice cream cone. What is the probability that in one particular set of observations, 10 out of 20 people are holding an ice cream cone? Okay. So first off, if you know what kind of distributions problem this is, go ahead and say it. This can be a little misleading because you might think it's Poisson because it sounds kind of like a Poisson problem, right? You're like, okay, there's this rate of people walking by, but notice we didn't give a span of time here, and it turns out that it's going to be a little more appropriate to use binomial. Great question. If we asked you this problem, would we give you the formula? Would we give you the PMF that's appropriate? We would. Yeah. Yes. So we wouldn't expect you to memorize the PMFs. We'll give those to you. This is not a Poisson problem, though. This, you could approximate it with Poisson, but this is more appropriately a binomial problem. Okay. So let's think of our P and our N and our K. So our probability that somebody is holding an ice cream cone is actually going to be just 2 out of 13, right? And that makes sense because we say on average 2 out of every 13 people that walks by is holding an ice cream cone. So that's our probability. Our N, well, we want to know out of 20 people, how many are holding an ice cream cone? Well, our N is 20, right? That's our number of trials, where each person is a trial. And then our K, our number of observations, is 10. So I'm going to go ahead and just write, first I'll snag a copy of the binomial PMF, and I'll code it really quick. Let's see if this has a good PMF here. This works. Well, let's see. Yeah, I'll just grab it from over here. Oops. Okay. So, let's see. P to the K times Q. See, that's the thing. Q is actually 1 minus P. So that's a little bit annoying. Let me just grab it out of our learn materials. I think it's important to look at these formulas and not just code them out in the form of Python. Let me find this really quick. Discrete probability distributions and binomial distribution, and this looks more like the way that I like to represent this. So I'm just going to grab it like this. All right. Q is the complement of P, and so often we'll see it written like that, but we might as well just write the complement of P when we're doing this. All right, so what do you need for binomial? Well, notice here we've got we've got combinations, and combinations requires factorial. So maybe what I'll do is I'll also grab the formula for combinations. And we know factorial, right? We don't need to think about that too much. So this is under, it's under conditional probability? No. Is it under basic probability? Yes. All right. So yep, no, yeah, there it is. Okay. So let's grab combinations. So we need to code out combinations, and in order to code out combinations, we need to code out factorial. And, I already answered one question like this, but I'll just say this outright. If we're going to ask you to code combinations or the binomial PMF, we're going to give you those formulas, so you don't have to memorize them, okay? First off, though, we'll need factorial, and I'll just say the factorial of n is, I'll just set an initial product. We do expect you to be able to code this offhand. So for each number in the range from 1, I could say 2, doesn't really matter, 1 to n plus 1, the product is going to be multiplicatively incremented by the number, and we're going to return the product. And then combinations is n factorial over n minus r factorial. I usually use k. N minus k factorial multiplied by k factorial. So let's write that. So def combinations. This is going to be n comma k, and it's going to be important for you to be able to write, translate from such a mathematical formula into code, right? That's something that you just want to feel comfortable doing within reason. We're not going to ask you anything that we haven't shown you. Okay, so here's factorial, here's combinations, and now we just need to write this last bit to the right, which is just p to the k multiplied by 1 minus p to the n minus k. And I often kind of lose track in writing this, so I might have to troubleshoot this a little bit. So n, k, and p is 0.5 by default. I usually set p to 0.5, coin flipping questions, whatever that might be. And I'm going to say, I'm just going to return the combinations of n, choose k. And I'm going to multiply that by, p to the k, p to the k. And I'm just going to give some separation here. I don't know why that put in a period. Multiplied by, we're going to have 1 minus p, right, the complement of p, to the n minus k, okay? And what was our question again? 2 out of every 13. What is the probability that 10 out of 20 people are holding an ice cream cone? So we've got our P, our N, and our K. We can just copy this. Oop. Let me just actually copy that. There we go. And I'm just going to pass those in. I'm just going to pass those values that we set above. And maybe I'll just be a little more explicit about this like that. Oop. Oh, I just deleted them all. Cool. Let me just get them back and do that again. Okay. So let's see what that gets us. So what is the probability that 10 out of 20 people are holding an ice cream cone? It's really low, right? It's 0.025 or 26, right? Percent, 0.026%. Okay. So that's just the takeaway here is if we give you some mathematical formulation, you know, try to be able to write code out of it. You know, recognizing in the binomial PMF, recognizing that that's combinations is a good thing. We may not ask you that directly in a technical interview, but it is good to be able to recognize that. If you want review on binomial, we definitely have those materials in Learn, and we're not going to ask you anything beyond that. Now, we might ask you some things related to binary, and I'm going to just show you a quick function to generate some binary. And if you've been in the premium prep classes, you've noticed this before, right? So let's go ahead and just look at this. Def, I'm going to say generate binary list, and this is going to be of length by default 8. So what we're hoping to get out of this is a binary list, which is going to be just zeros and ones, right? That might look something like this, but it's going to be random, right? Let's see, I imported random already, but I'll just grab it again to reinforce that you will probably need to use this at some point. So from random import choice, and I'm going to generate a random list. I'm going to say I'll just make something called out, and I'll say let's say whatever in range 8, which will be range of the length. We'll just say out.append, and then it's going to be the choice between 0 and 1. So that's what choice does. Choice just chooses an item from within a list, and pretty simple, right? This is going to give us this is going to randomly append to out. It's going to randomly append a 0 or 1. Okay. So now I'm going to just return out like that. And let's go ahead and test that. I'll say generate binary list, and let's just use, well, let's do length of 16 just to do that. And notice this is random as our computer allows, which is pretty random, effectively random for our purposes. Now, we can start asking some questions about this, you know, like what is the probability of getting 4 ones? And that's something that, you know, if we keep running this, we're going to get, at times, we're going to get 4 ones, you know, sort of interspersed across all the zeros. But how could we, using this approach, how could we give a definitive probability that we're going to get all ones? Sorry, get 4 ones. There's a couple ways we could go about this, all right? There's a couple ways. We could say this is 16 trials, right? And we could just grab the binomial PMF, and we could, you know, say, okay, well, n is 16 trials. we're asking what is the probability of getting 4 ones, and we have a probability of 0.5, right? We're either going to get a 0 or a 1. They are equally weighted, and we should just be able to give an answer. Okay, well, the probability that we're going to get 4 ones out of 16 trials between 0 and 1 is 2.8%, roughly 0.027, right? Now, what if we didn't understand that the list that was given here was generated through a binomial process, right? This is purely binomial. This is a series of independent trials. None of these values are going to affect one of the other values, right? So we can call this binomial with a probability of 0.5. But what if we didn't know, right? What if we had more than 2 values here? And why don't we do that in a second? Here we only have 2 values, but what if we had 5 values and we were asking what is the probability of getting 4 ones? Then we would want to take a different approach to determining this probability. And I would likely start off with sampling some number of times from this generate binary list and returning the sum of ones. Okay? So I'm going to do this in a couple ways. Well, no, I'll just do it in one way. So I'll call this, I'll make something called analyze bin list dictionary. So what this is going to do, and let's say a number of trials. And by default, we'll do 1,000 trials. And let's also do a length of the binary list. So usually we'll call this n, right? I'm just going to default this to 16 because that's what we're considering. And I'm going to say, okay, well, we have some dictionary. And I'm going to call out to this a certain number of times, num trials times, 1,000 times. And that's going to give us, we're going to pack in this dictionary, okay? We're going to pack in the dictionary, and that's, yeah, that should just work. So let's think about how to do this. I'm going to say for whatever in range, the number of trials, and I'm going to say, I'm going to call out to generate binary list. And we'll use the length that we passed in up here. And I'll just put this into something called ones count, right? And I'm just going to sum the ones in here. Now I could do it like that, but maybe I want to do it like this. Maybe I want to do dot count of the ones. Either way is valid, and I'm going to go with this because I'm going to kind of change this function a little bit to maybe be more interesting or at least be more complex. So our ones count is like that. And I'm going to say if the ones count is not in the dictionary, let's put it in the dictionary. So d sub ones count is going to start off with a 0 value, and then I'm going to increment it, and that's going to get us something. So I'm going to return the dictionary. And now if I run this, I'll run it with the default parameters. And notice it's all out of order, which is fine. It might be nicer to look at this in order. And for that reason, I'm probably going to just say for key value in the sorted version of this. And I need to call dot items because it's a dictionary. Maybe I'll just open this up a little bit more so it all fits. So let's say I do that. I'm going to print, you know, if you've been in class, you've seen me do this a million times. I'm going to print the key and the value. And notice we have counts for each of these values. Now, maybe I'm going to run this over and over again, and we're going to get different counts. Oops. I'm just adding more space. If you're in a Jupyter Notebook, Shift-Enter will take you to the next cell, but Control-Enter will run it in place. So notice 36, 21, 25, 25, 30, 25, 29. We could do that all day. If we want probabilities here, then what we should do is divide by the number of trials, okay, for each value. So I'm going to take num trials. I'm going to just pull this out, and that way we have it accessible so that we can divide our values by the number of trials. Okay. Oop. Oh, well, that makes sense. Okay. So we get 0.03 for 4. Let's just remember what we got up here, right? From the closed form. This is not a sampling approach. We got a probability of 0.027, 0.0278. Let's see what we get if we run this over and over again. 0.025, okay, that looks like it's in the neighborhood. 0.033 in the neighborhood. 0.027, 0.019, 0.021. This seems reasonable, right? And it definitely seems reasonable, and I think we could make this a little bit more solid through a couple mechanisms. The mechanism I'm going to prefer here is to transform this dictionary a little bit further, right? So I'm going to change this up a little bit, and I'm going to write another function. And I'm going to call out to the analyze bin list dictionary function now. So notice this analyze bin list dictionary is calling out to generate binary list. Now I'm going to do a certain number of trials against the analyze bin list dictionary function. So I'm going to call this analyze, oh gosh, what am I going to, so let's call this verify, let's call it converge binomial. I don't know, just call it that. And I'm going to put in a length again, why not? Length of 16 by default, and let's say the number of experiments. I'm gonna, I don't know if 10,000 is too much, but I'll go ahead with 10,000, why not? Okay, so now what we can do is call out to, we're gonna make another dictionary, right? And I'm gonna call out to this analyze bin list dictionary a certain number of times. So I'm gonna say for whatever in range the number of experiments now. And I'm gonna put in the length, and I'll leave number of trials as the default. Let's just assume that that's fine, okay? So I'm gonna put this into something called results dictionary, and I'm going to say for each item in the results dictionary, I'm going to put those into, append each value into our original dictionary, okay? So I'm gonna say for key value in the results dictionary, dot items, I'm gonna say if the key is not in D, I'm going to initialize a list in D. Okay, so I'm going to say D sub K is going to be an empty list, and then I'm going to just say D sub K is going to have appended to it V. Okay, so let's take a look at what this looks like. It'll be a little messy when I print it out, but we'll try to make it look, I don't know, okay. So I'm going to return the dictionary, and I'll just say, nope, I guess I didn't save it. So for key value, in, why don't I pull this out of here? For key value in d.items, let's look at, remember the values are lists, right? So I'm going to print, I'm going to print the key and the value, but I'm not going to print all the values. I'm just going to print the first 20 of them or something. So I'll just say key and V, remember this is a list. I'll go up to, I'll do the first 20, and let's see if that works. In number of experience, for whatever in range, I'm missing a colon. So notice this is going to take a little while to run. I may have, 10,000 might be too many times, really, but we'll see. We'll see how quickly this runs. I can also kill the kernel and start it back up and just do 1,000. So notice how many how many loops we're actually doing here. It's kind of a lot. So every time we run analyze bin list, we're doing 1,000 trials, right? There's 1,000 loops in there. So we're looping 10,000 times with 1,000 loops in there. And then we have this secondary loop, which is really not consequential given all the looping we're already doing. You know what? Let's go ahead and let's restart the kernel, and I'll lower this to 1,000 experiments, and let's see if that does okay. So I'll just run everything again. So cell, run all, and this should, I think this will get us there quicker. Oh, there we go. Okay. Oh shoot, you know what? I need to sort this. And maybe what I'll do is, instead of showing the first 20, I'm going to show the first 10. Otherwise, it's going to look pretty messy. And then I'll do ... here. Look a little nicer. There we go. So here we're basically going to have a certain number of so here are different counts for the values of k, right? And these are we can take these and average them to get the average number of counts, right? So simply we could say, let's take the sum of everything in V, right? And divide it by the length of V. So this is going to get us the average counts, and I'm going to cast this to an integer. Well, no, I'm going to leave it as a float. So now we'll take a look. I don't need these this ellipsis here. Now we'll take a look at the average number of trials for each of these, okay? And of course, given that this is binomial, the highest counts are for 8, right? Because that's our expectation for 16 trials, is 8 successes if we've got 0.5 probability. And notice that it's looking more and more symmetrical, right? 174 and 174, 122 and 122, 66 and 66, 27 and 27. These are pretty close to each other, right? So, you know, on average, the average for 1,000 of these experiments is, you know, on this dictionary that's calling out 1,000 times is a count of 27 point something for a k of 4. So we can take this and turn it into a probability, right? We can just take this probability, and since we're considering a number of experiments a number of trials equaling 1,000, let's just take this whole thing and divide it by 1,000. And that should give us our probabilities. Let's see how close we get to the actual binomial PMF. So this runs in like 10 seconds, maybe something like that. So notice, this is pretty close, right? This is pretty good. And this isn't, you know, I'm not trying to say that this is exactly what you're going to do on the technical interview. I'm not saying that. But I want you to understand that there's sort of a verification going on here. I am verifying in some way that this process is binomial through a sampling paradigm, right? I'm sampling out, and then I am, you know, converging my results in order to average the counts, and then I can divide the average count by the number of trials, and that will get me a probability that looks a lot like what we get from the binomial PMF, right? So 0.0278 versus 0.0277, but that could round to 8, right? If we're considering, you know, just this level of precision, this is the same number, right? If we're rounding, that is the same number. So that's pretty good, and it didn't take us long to figure that out. Okay, so let's kind of pivot this a little bit and drive, you know, maybe drive the idea home a little bit more. So let's say we're not generating a random binary list. Let's do this a little differently. Let's say we have, let's say we're choosing from 0, 1, 4, 7, and 11, okay? And this is going to get us a completely different list. So let's generate a weird list. And we're still generating it from a length of some sort, right? Length is 8 here. And we'll think about this. So this gets us something that looks like this. We might ask a couple different questions in this regard. And notice that our binomial PMF is no longer relevant here. We can't use the binomial PMF to answer this because this is a stranger problem now. And I'm going to make it even a little bit stranger. Instead of counting the ones, I'm going to sum the list. All right? So, you know, before when we were considering binary, the count of the ones and the sum of the binary list were the same thing. Yeah, let me just go ahead and change this, and we'll consider how this changes this, you know, this thing that we're making. Now, this could be anything, right? This isn't, this doesn't have to be something that exists formally. We're looking at a random process and the result of a random experiment. The random experiment here is going to be the sum of the values, considering these are base 10, the sum of the values in this list. So I'm going to analyze this weird list, and I'm just going to keep the rest of these things the same. So instead of a ones count, we're going to say, I don't know, call it the weird sum, and I'll say this is the sum of the function call, which is generate weird list, right? The sum of that. and I'm going to say if the weird sum is not in the dictionary, then d sub weird sum gets 0, and then I increment it by 1. And so instead of converging binomial, I'm going to converge the weird sum, and for whatever in range the number of experiments, the resulting dictionary gets this analyze weird list dictionary of whatever length. And I'm going to say for key value in the resulting dictionary, if key not in dictionary, etc., that all makes sense. So instead of converging the binomial, I'm going to converge the weird sum, and we're going to ask a different sort of question, or we're going to be able to answer different sorts of questions. Now, we don't know an effective PMF offhand to perform this. And so I can't compare this to something that already exists like I did with the binomial PMF, but consider that it worked for the binomial PMF, right? So this sampling approach worked to generate a probability that was in convergence, relative convergence with the results of the binomial PMF. So we can do this. We're going to assume we can do this for this weird generator that I've created, right? This weird list generator where we're thinking in terms of the sum of these results. So we just invented some phenomenon, and we're going to play around with it. We're going to see what the result is. So we converge the weird sum, and I believe all of this should be good. And we're going to look at the probabilities that result. And I think this shouldn't take any longer, or not significantly longer. Nope. And of course, this is going to be a a longer dictionary, right? Because we've got this number 11 in there, and 7 and 4. It's not just the sum of ones, right? We've got 4, 7, and 11 in there. And looking at this, at no point did we get all zeros, right? That didn't happen. At some point, we either got 1, 7, and or we got 7 ones, or we got a 4 and 3 ones, right? We can start thinking about how we get to certain results. And at some point, we either got 11 ones, or a 4 and a 7, or, well, that's it. Or a single 11 and all zeros, right? And that happened. Whatever version of events that happened. And we can kind of look at this, and we can ask questions. We can start trying to answer questions. We can say, well, approximately how many... Sorry, let me think of the question in an effective way. Approximately how many times, approximately what is the probability that you're going to get 42 out of, as a sum resulting from this 16 place list generated from this weird set of values? And we can say, well, what did I say, 42? 44? Oh gosh. I don't remember the number I said, but it doesn't matter. Let's say it was 44. How many times are we going to get 44? Well, we could say kind of looks like it's 0.5% of the time, roughly, right? And we could take this further. And this is going a little bit beyond the scope of the technical interview. But this is getting into the machine learning space. We don't know. We don't have a PMF here. We don't know what that is. And that's really okay, because we've got this sampling approach that will allow us to at least attempt to answer these questions, right? We can at least attempt to answer these questions. What is the probability that we're going to get a sum from this weird list that looks like 67? Well, 2.25% maybe? Probably, And we're not quantifying our uncertainty, but we're assuming that this is a somewhat effective approach. We can also glean from this our potential expectations. And we can think about those, right? So the highest value I see so far, and I might be wrong. No, I don't think I'm wrong. I'm thinking, let me see if there's something higher in this direction. 73. 73 looks like it's our mode. That looks like possibly what our expectation is from this function, this PMF, that we're not familiar with at this point. We don't know what that looks like. Now, you can imagine if you built a data set where each value here, like 0, 7, 8, 9, if we consider all of these to be possibilities, this could be the row, and this outcome could be the, let me say this in a better way. Each one of these numbers could be a column in a table of data, and this is one row of values, right? The probabilities corresponding to each of these. And if we did this, let's say we did 5,000 rows of this, we could then put that through then we've got X and Y values, right? We've got a data set from which we can attempt to extrapolate a function. And especially if there is some linear function underlying this, and I assume there is. I don't know that there is, but I assume there is. I think I do know that there is. If there's a linear function underlying this, we might be able to just arrive at that with a linear regression that will give us coefficients. But my assumption is it's going to be fairly complex, and we may not be able to disambiguate it, but we could build a machine learning model that will be able to predict the outcomes of this kind of data, right? And so this is that's getting further than what we would consider in the technical interview, but this is just to show you, really, that you can start with some kind of random process, right? Here we've got some kind of random process. And we have a generalized approach to determining to trying to approximate the probability of given outcomes, right? So this is not binomial, it's not Poisson, it's not anything like that, but it is a legitimate random process, and this is a way to analyze it, this dictionary approach. So we can generate a single dictionary for a series of trials, but then we can narrow in our probabilities using this convergence function. Again, this is a little bit above the level of the technical interview, and that's where we like to teach, just slightly, because when you get to the technical interview, it won't be quite this inceptioned, I guess you could say. Right, this is analysis within analysis. But so if there are any questions about that, please let me know. I'm going to throw another problem up here that kind of takes us back to something a little bit simpler to think about. But definitely feel free to ask questions about this. Okay, so I'm going to put up another probability problem, kind of a distributions problem. And, as I'm asking it, feel free to put in there in the Slack what kind of problem you think it is. So I'm going to say 90 people walk through. Oh, let me answer this question. If the warm-up functions end up getting used in the actual challenge, would you tell us if there is an error in our warm-up functions? Absolutely. Yep. Yeah, and we won't let you go forward if there is an error in the warm-up function. And if you struggle in... Oh, yeah, I can post that code. If you struggle with a function and we help you significantly, there are going to be times where we might even solve that function for you. But that's usually a sort of a moderate to severe assist. So you want to try to solve your own functions. Maybe that's obvious. Maybe that goes without saying. But we're not going to let you proceed with a broken function. So let me grab, yeah, I'll grab all of this and throw it into the Slack. And keep in mind, you know, this is definitely different from what's on the technical interview, but it's more the way of thinking about the problem, you know, and that's kind of what I'm getting at here. And we'll take that approach a second time, I think, before we wrap up today, and it'll look a little different. So there's that. That should just run if you want to run that locally. Okay. So let's think about another problem. 90 people walk through let's say some mall doors in the afternoon. Oh, mall door through some 90 people walk through some mall doors in 30 minutes on average any given afternoon. So notice built into this, there's an assumption that you know, it's not going to be different on the weekends, or that seasonality doesn't matter. Those kinds of questions are important. I'm just kind of giving you those constraints offhand. So let's ask the question, what is the probability that we're doing 90 and 30 minutes. Let's do 100 people walk through the mall doors in 40 minutes. So what's the kind of distribution? Yep, a couple people chimed in. It's Poisson. So what is the lambda that we're going to pass into the Poisson PMF? I'm sorry, I'm just waiting for, for somebody to give the lambda. We know what the K is, right? I'll just say K is 100, right? What is our lambda for 40 minutes? It's going to be some transformation of 90, right? So it's going to be 90 times something. So we're going to take 90 and we're going to modify it in some way, right? If we're going from 30 minutes to 40 minutes, you know, we can represent this in a couple ways. And maybe this will kind of clear it up. I'll just write some of the tech here. So there's going to be 360 divided by 30. Is that what that is? See, I think about it as I'll just do this. I just think about it as 90 times 4/3, right? 90 times 40 over 30. So you know, let's take a look at what that is. And I'm not saying that that's different. I just, in my head, that makes sense. So 120, 360 divided by 30, exactly, it's 120. Okay, awesome. So our lambda is 120. And I'll just grab that. Our K is 100. And I'll just code our functions really quick that we'll need in order to answer this. In order, you know. So I think I wrote a factorial function up there, so we don't need to write that. I'm just going to say Poisson PMF, and oh, I should just grab this, the formula. I should always remember to do this. Iteration. Oh, those are practice problems. Discrete and Poisson. Okay. So let's just write this. Super simple function to write. Notice we need our lambda and we need a value for k. And I usually write this in a different order. I do e to the negative lambda times lambda to the k. It doesn't matter, obviously. It's just, you know, when you sync it into your mind, however you write it, you just tend to always write it that way. We need e for this. We need Euler's number. So I'll just say from math, import e. I could hard code it. What is it, 2.71828? Euler's number, 2.71828. Yeah. But you might as well just grab it from math. So I'm going to say this is going to be lambda to the k multiplied by e to the negative lambda divided by the factorial of k. And even though you don't need to do this, I always do this, not for, you know, just for separation of the ideas, I guess, not for any reason, not out of any necessity. So if we want to answer this question, we can just plug in our numbers, lambda and k, and what we're answering here is what is the probability that 100 people walk through the mall doors in 40 minutes, right? So that is 0.0068, right, or roughly 0.68%. Now, notice the skill we used here. It was really just building our new lambda. Because at the end of the day, this function is easy enough to write. If you're given this formulation over here, like, it's really, you know, you need to know how to import e, or hard code it directly, that's fine too. You need to know how to import e, and you need to know how to call out to factorial, or write factorial and call out to it. And then you just return the result of this operation. So that's easy. The part where people get stuck is really this, you know, calculating your lambda. More often than not, that's what I see. So let's think about Poisson. We've got this Poisson PMF. And let's sort of, let's do stuff with it, because we have it. Let's make, let's write, yeah, let's just write a dictionary. Simple enough. Let's say, let's write something called the Poisson dictionary, and we'll pass in a lambda, and we'll pass in a low value of k and a high value of k. If you were in the premium prep classes, you've seen this. You have this code base essentially. So this is going to be easy enough. We'll just make a dictionary, and we'll say for for k in range, we're going to go from low k to high k. And just offhand, I'm going to be inclusive of high k. Doesn't make the hugest difference. It's just we're assuming inclusive because we're considering k, right? It's, you know, you could do this in an exclusive way and it shouldn't matter. But specifically, we're being inclusive of it. Notice I don't need to check for membership of k, because I am going to just set the initial value here with the return from Poisson. So Poisson PMF lambda k. And that's going to, yeah, that's just going to work for us. So we can just return the dictionary, and I'll just say for key value in the Poisson dictionary, dot call out to it dot items, and I'm going to do, I mean, we could use this lambda. It's kind of a high lambda, really. I might make it something else. Let's say we have a lambda of 20. Okay, lambda of 20, and we're going from, let's go from 10 to 30. So we're kind of looking around our lambda. And I'll just print. Oops. I'll just print. I'll print k and v, and we can see our probabilities. So the highest probability is our expectation, right, of 20, our lambda of 20. And something that's always interesting about Poisson, 20 and 19 have the same probability. So that's kind of cool. I don't know if you've noticed that. You can do this for any lambda and you're going to get something like that. So we might change our question here a little bit, right? So here we're getting the results of, we're getting all these probabilities in some range. But what if we are trying to determine the number of counts we would expect from a phenomenon that's out in the world that follows a Poisson distribution? So maybe the story we're telling here is, in 1 hour, on average, we see 20 Canada gooses, and that's a Letterkenny reference. Woo! Okay. Quick aside, I was overhearing a city council meeting the other day that someone in my house was attending remotely, and a bunch of people got together and were working really hard to prevent the city of Denver from starting to, I guess, kill Canada geese. And it reminded me so much of this Letterkenny episode. And I was also thinking, if this is the most important thing that's going on for people, great. I'm not going to judge. Let me just say that. I'm not going to judge. But there was like, I think there was like 15 people, and they had organized to fight for the Canada geese, which I'm all for. I was just surprised. And it was funny, over and over again, these impassioned essays that people had written and were reciting to the city council, and just made me wonder, what it's like to be a city council member and listen to everybody's, anyway, that quick aside. So in 1 hour, on average, we see 20 Canada gooses walk by in City Park. Let's say we expect to see 20 Canada gooses walk by in City Park. I said within 1 hour. Okay, so assume this rate is constant for any day, for any given day of the year, and ongoing. And let's ask the question, what is your expected count of Canada gooses? I know it's geese. What is your expected count of Canada gooses in over 10,000 observational days? Let's say it like that. So it turns out this is really easy to figure out. And we can just grab this Poisson dictionary function, and let's call this expected observations. And our lambda is 20, right? We're just going to keep our lambda at 20. And we can keep the low k and high k, that's fine. I'm going to, instead of building this dictionary in this way, I can instead just call out to our original Poisson dictionary. And this is going to give us probabilities, right? These are theoretical probabilities that are returned. So the key is the k value, the v is the theoretical probability. We can then traverse this dictionary. We can say for, maybe I'll make another dictionary, just to really be clear about this. We can traverse D. So I'm going to say, instead of this for loop, I'm going to say for key value in D.items, D sub out is going to get the key, right? So again, we don't need to check for membership here. Oh, sorry, I need a third thing. Number of trials, or yeah, let's just say number of observations. Right, that was, I think I said 10,000. Yeah, I definitely did. So all we need to do in order to state an expectation given the probability is multiply the probability by the number of observations. And that's all that looks like. We can just do V times 10,000. And let's see if I have this key value. I'll just grab that. At some point, you know, I've written the same thing too many times. And let's do that. And I'm going to say 30, and let's just do number of observations as they are. That's fine. And I'm going to grab, I'll grab this over here. And this is only to prove a point that I'm grabbing this, and or to illustrate a point. Okay. So if I run this, notice that we get, oh, what's happening? Expected observations. I'm returning D, not D out. That's why. Okay. So notice I'm getting partial counts. That's fine, but I'm likely going to round this, right? In this case, let's just say I'm going to round it. I could even put it to the floor, right? So 342.98 could just be 342. But I think for this, I'll just round it. I'll say round this value, and let's see what happens. So notice, you know, 58, 387, blah, 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 844, 669. Now, these are counts, right? These are our expected counts. And I can take this, and we can consider, we've got our original probabilities over here, right? We've got all these probabilities, and these are theoretical, and then these are theoretical expected observations. Now, notice these are theoretical, right? They are not what would happen if we went out and actually did this, right? This is what we would expect to see given our lambda. There's a question. Let me answer that. Would it matter that the lambda is per hour, but the question is for days? Would you need to multiply the lambda by 24 hours in the day? Oh, sorry. That's just I kind of wrote that in a somewhat unclear way. Number of observations is going to be sort of 10,000 times that you go and observe for 1 hour, right? So can reduce over 10,000, I'll just say observations instead of 10,000, let's say 1 hour observations. Yeah, I hope that clarifies it. Sorry, yeah, observational days sort of implies that we're observing for 24 hours, and that's not what I meant. I meant 10,000 different days where, you know, maybe you've got a team and they're all sitting down somewhere and they're observing for 1 hour at a time, and they're writing down what the count that they observe. So in reality, you know, in real life, that would be a random process, or there would be a random result, and we wouldn't see something quite so clean as this. But if we were trying to verify that something was Poisson, I guess you could say, if we're trying to verify that something was Poisson, we would perform this whole thing over and over again, like the actual random, the real world random variable that represents the number of Canada geese that walk by you in a certain amount within an hour. We would do that, and we would do that over and over again, and then we would average those counts and compare them to this theoretical output. So that's one reasonable way forward. Something we might consider here, though, is we are losing some information. There's a concept of information loss, and here it's going to be because of precision. So if I take these values, if I take all the values from our returned items here, and maybe I'll just write a quick function to illustrate this. Yeah, I'll write a quick function. So let's write something called, and I'll probably wrap up after this, expected observations, and then I'm going to call this probs from expected observations. And let's just leave, we'll just leave these same values, I guess. Number of observations, 10,000, sure. So now I'm going to grab this, I'm going to build a dictionary from our expected observations, right? And that's just going to take those same values, and I'm going to get the dictionary from that. And what I'll do here is, I'll make this d out, and I'll say for key value in d.items, we're going to take each of these values and divide it by, you might be tempted to divide by the number of observations, and that's not entirely wrong. That's not wrong. But we might need to divide by 9,999 potentially. There's a chance. And so I'm actually going to divide by the sum of the values in this. So what I'll do is d sub out sub key, right, is going to get the value divided by the sum of d dot values. Is that right? I think that's right. So let's just return d and c, and then we'll compare our probabilities and see how close we're actually getting with those. So I'll just grab this, and I'm calling out to this function now, but I'm going to keep all of those arguments as they are. Oh, did I call this on 10,000? Yeah, I did. Okay, great. So this should get us, we're looking at the range from 10 to 30. This should get us something parallel to this dictionary we're seeing over here. Oh, whoops. I am not returning d sub out. I'm returning d. Okay. So notice these are different. These values are different. And you know, if we need to explain why these are different, what, 0059, 0058, but they're different, but they're not that different, right? They're close. They're close. And if we need to explain why they're different, it's just that we've lost some information in this process. We lose information in this rounding right here. So we kind of, we have decreased our precision, and that's okay, right? Because we're still getting pretty close for most of these values, pretty much for all of them. You know, some of them look a little further, but we're never, you know, we're never more than 0.02 of a place off. But it's important to be able to explain this, and I think part of explaining this is to give a clue into the kind of discrete nature of computers in general, right? Where we cannot hold infinite precision in a computer. We can't, and we have to be okay with that. We can build algorithms that can get us really high precision, but we also want to understand the meaning, whether or not that precision is meaningful. And, how do you think we might migrate the results of this toward the theoretical probability? So this sort of, information loss probability here, how would we get that closer to our theoretical probability? The question, honestly, is not, it's not too difficult and to answer. I just noticed something a little wrong with my code here. Number of observations. I shouldn't be multiplying by 10,000. I should be multiplying by number of observations. Let me just verify. Yeah, everything else is good. So if we want to have closer probability values in our, after this transformation, all we really need to do is increase the number of observations. So I'm going to change that to 100,000, and we should get a little bit closer. Let's find out. Oh, did that work? Oh, I didn't rerun this code. Here we go. We need to do that. Let me just make sure everything else is okay. Yep, okay. Okay. So let's see if we did any better. We might still be subject to the same rounding error, actually. Nope, we're getting a little closer. So before, when we did 10,000 observations, this is 0.0108, and now with 100,000, it's 0.0107. So yeah. So that's it for me today. This is just sort of a look into the kinds of things that you might do on the technical interview. And why don't I paste in this code really quick? It's easy enough to do. You're going to need factorial at some point. And we'll just put that here. Okay. And even though I'm not including the problems here, if you want the actual written problems, I just made these up. Make up problems on your own, right? I think that's a really good way to build a very solid foundation in these kinds of distributions, because it's really about this story you're telling, and you can just rewrite almost any one of these problems to be a somewhat different story. And just grab this one too. But the process in that story is the same. The process is the same, and if you keep the same values, then the outcome is the same. Is that it? That's it. Okay. All right. Thanks so much, everybody, and I'll check this video in a couple minutes to see if YouTube will let me add it to the playlist. Sometimes it doesn't let me do that right away. Yeah, I will. If you're in Premium Prep, I'll see you on Saturday, and we're going to be doing something like this, like what we looked at today. More problems, more practice, different problems. I've got sort of a battery of problems that I've been working on that look different from what we just looked at. Not too much different, but different stories, different kinds of random processes. And even though Premium Prep is ending for this round on Saturday, we're going to continue having study halls for the next 2 weeks, and that will just continue. And we'll continue through the next Premium Prep for sure. We might have to remove one day as we approach the interview deadline, just so that we can do more interviews, right? But I'm going to hopefully not have to stop doing this. We'd probably cut Friday or something like that, but hopefully not, because definitely want to help all of you get there if you want to get there. So thanks so much.